Hi there! Today on the bench we have a Ten-Tec Eagle amateur transceiver. The owner dropped this transceiver off claiming that there is no RF output power. So, just like in all the other videos, sit back and relax and we'll go through the troubleshooting procedure together and we'll figure out why this thing isn't putting out any RF. So, let's get right into it. We're now ready to perform some preliminary tests with this Ten-Tec Eagle, and the very first thing that we want to do is verify what we've been told. Now, we've been told that this Ten-Tec Eagle does not transmit, but it does receive. So we haven't turned this thing on at this point, and we really don't know what it's going to do. We could turn it on and smoke's going to pour out of this thing, or it could go right into full transmit mode. So we really have no control over if this thing is going to smoke or not at this point, but we do have the option to put this into a dummy load to make sure that if this thing does go into full transmit mode, it's not going to transmit into nothing, and the radio will not see a high SWR condition. A high SWR condition, or standing wave ratio condition, will cause the RF output section in this transceiver to get very hot and cause issues. Now, a lot of these modern transceivers will shut themselves down if the SWR goes high, or it just won't put out any kind of power. But we don't know if the processor in this thing is confused or what really is going on in this. Again, we haven't turned it on yet. So let's just be careful and take some precautions here. Another really good thing to do is to have the line cord fused. Have a really good fuse in the line cord just in case this thing goes, absolutely haywire. So I've got this hooked up into my Marconi Instruments 2955B, and this thing will display transmit frequency, output power, and it'll also show any kind of modulation that we're going to have if we grab the microphone and talk into it. So what we're going to do is turn this thing on. I'm going to keep my fingers on the on switch here just in case something goes crazy with this thing and I can click it off right away really quick. So here we go. Let's look for a normal startup. Looks pretty good so far. And so far it's looking like it's just trying to receive. So there's no transmit light on. There's a little transmit light down here. It's not lit up. Alright, it is in the AM mode. The bandwidth looks wide. It is. The power looks like it's set high to 100, so when I do grab the push to talk and press the little button here, we should get some power on AM if the radio is working correctly. It's set to 3.7 megahertz. So since it's hooked up to this unit right now, let's test the transmit section first, and then after that, let's test the receive section to make sure it is actually receiving. So I'll grab the mic, I'll push the button, we'll look at the front of the radio, make sure everything looks normal, and we'll also watch the scope back here. So here we go. Alright, I'm pressing the button. We can see that the TX lamp is on. I'll talk into the microphone just a little bit here. We can see that the ALC lamp is flashing so that we know that there is some form of audio inside the radio. So it's getting through the microphone and into the radio right now. And I'm talking to the mic and I just saw a little flicker on the screen there, but not very much. So test, test, 1, 2, 3, 1, 2, 3, test, test. And we can see every now and then we get a little bit of a flicker of audio happening. And we get very, very low output power happening here. But there is a little bit of, oh, there we go. There's a little bit of power coming out or trying to get out of the transceiver right now. So already this is kind of painting a picture for me, and I'll explain that here quite shortly. So now what we want to do is, we're at 3.7 megahertz here. We want to see if the receive section is working. So what I'm going to do is unhook this. I'm going to move my signal generator up on the top here, which you can't see. It's the knob I'm spinning there. To 3.7 megahertz, I have 10 microvolts of RF output, and there's a 600 hertz tone on the 3.7 megahertz signal. So we should hear that on the receiver. I'm just going to take my alligator clips and couple them to this PL259 here, like so, and we should see a signal when I attach this. And there's a signal there. So it's 7 S units or thereabouts with a 10 microvolt signal coming into the receiver. So it looks like the receive section is working just fine. Now I'll turn the modulation off here. Turn it back on. So it does have receive at 10 microvolts. That's working pretty well for 7 S units. Just disconnect this here. So I'll just shut this off. So really what this is telling us now is what we've been told is true. It does have receive, but it just doesn't have any transmitted output. So already this is pointing to either the driver or the RF output transistors in this transceiver. So the fact that we do see just a little bit of power here and we do see modulation is a really good indication that the driver section is probably working and the RF output transistors are probably damaged. So what causes damage to the RF output section in these transceivers is high SWR conditions, like open antenna connection, or if this is hooked into an antenna tuner and the antenna tuner is mistuned, that usually damages the RF outputs in here. So what we're going to do now is we're just going to take this thing apart and we'll go through with an oscilloscope and go section by section, and we'll look to see where the RF signal stops, and at that point we'll verify what the problem is. So I'll just take the lid off and turn the scope on, and I'll be right back. Here we are inside this Ten-Tec Eagle transceiver. Now this is with the upper lid removed. This is the lid with the speaker on it. It's very easy to get in. You take off 4 screws, 2 on each side, lift the lid. There's a little white connector that goes right down in here that connects to the speaker. Just remove that and the whole lid comes off and you're inside. Now before you go about taking the lid off of any transceiver, you want to make sure that the power is disconnected in the rear, just in case you tilt the lid and touch the circuit board or drop a screw inside or do something like that. That would cause a lot of damage in this. So just got to make sure that everything is disconnected at that point. Now, in order for us to find the issues in this, we need to have power applied to it. And in order to work on a radio or do anything with any kind of 12 volts or any power applied to anything, you really need to know what you're doing. So if you're following along, you're doing so at your own risk. Just take care. So this area here is the output section. These are the 2 final transistors. These are 2SC2782s. There's one here and one here. And this is the driver section here. These both are RD16HHF1s. These are MOSFET drivers right here. And there's another RD16HHF1 here. So really, the trail of RF is kind of like this into this area. So what we need to do is we need to find out where that RF is going missing. Now, if you recall, when we looked at the screen on the analyzer just over here, which was this analyzer here, I'll just show you again. That analyzer right there, we saw that we did have a little bit of modulation when I talked in the microphone, and it did show a little bit of power. So that kind of makes me think that, the driver section in here is probably working at that point, and it's probably getting lost in this area. So the most common problem with these transceivers when they go bad really is these transistors right here. It's a very, very common thing, again, due to high SWR or, a mistuned external antenna tuner or something like that. Something has caused these things to go bad. And in a case, where it's a really bad failure, sometimes it will also take out the drivers. So that's what we're going to do. We're going to kind of go between the 2 sections, and that'll kind of give us an idea of what's going on, and we'll know whether to go this way towards the outputs or this way towards the drivers to find the problem. So what I'm going to do is reposition the camera and we'll start troubleshooting. We're ready to troubleshoot the RF section in this Ten-Tec Eagle. So again, the RF path here is coming out of this board, going through this cable into the driver board down here. These are the 2 FETs heat sunk to the side of the radio. The signal comes out of this board, goes through this cable into this board here. This is the RF output amplifier. The signal goes into these transistors, and then, of course, on the collectors here, we have a much larger signal going into this transformer and out to the antenna, and that really is the RF path. So after this transformer, we have another board and some smaller associated circuitry, but we're not going to worry about that right now. We're just going to focus on this area and try and locate our issues. So before we go into actually looking for an RF signal with an oscilloscope here, we want to do the simple things first, and we want to make sure that there actually is a supply voltage on these transistors, because if there is no supply voltage, we're not going to have any RF output power. And the way that these transistors work is really quite simple. On this side here, we have, this is the base lead, this is where the signal goes in the center, and this is where the signal comes out on the collector on this side. The 4 corners, these 4 leads are all the emitters, and they're just tied to ground. So these are NPN transistors. All right, so we have emitter, base emitter, emitter, collector emitter on each side of this transistor. Same thing for this one, emitter, base emitter, emitter, collector emitter. So signal in on this side, signal out on this side. Really quite simple to test these transistors. So when we turn the radio on, we should have a supply voltage, whatever our supply voltage is. If you have a power supply powering your radio, the supply voltage should be present on this pin right here when you turn the radio on. Now, a word of caution, if you're using a probe, you don't want to slip. This is plastic here. But you don't want to slip and do this and touch this to this pin here, because you're going to get a mighty large flash if you have any current coming in from your power supply, and you're going to destroy this board and add more problems to what's already there. So you need to be very careful. If you're following along, you're doing so at your own risk. Just take care. You want to come in nice and square and do not slip and touch any of these emitters, because this is positive here, all right, and then this is direct ground on each side of this pin, so any kind of connection between here is going to create some very, very large issues. Now, through the transformer, if you're going to use a DC ohm meter, this is going to look like a dead short from this collector to this collector here. All right, so we really only need to just check one of these things. If there is an open connection between this collector and this collector here on this transistor, you have some very, very big issues, and that's a very, very rare a failure point situation on this. You would see some pretty big charring on the board if something had opened. All right, so we really only need to probe one collector, and that's going to tell us that there is voltage on the board. Of course, if you do have a really big charred hole in your board here, anything could be the issue at that time. But this board looks to be in very, very good condition. It doesn't look like anybody's been in here, touched anything. If there are any failure points in here, they look like they would be pretty fresh. So what I'm going to do is turn the power on the radio, and I'm going to take my voltmeter probe and I'm going to touch the collector. Now, I don't want to do this with the microphone push-to-talk button applied. We want to do this with the radio in the receive mode. So we don't. If you have a CW key, you don't want to have the radio keyed. We want no carrier at this point. We're just looking for DC voltage on the collector here to make sure that there is supply voltage coming in this red lead into this board. So this is my probe lead here, and I'm going to come in and touch that collector lead, but I'm going to focus the camera on the voltmeter here, and we'll see what goes on. So I'll turn the radio on. All right. And I think my power supply is in the 13 volt range somewhere. So I'll just touch the collector here. All right. So we have 13.7 volts there. So we know that this board and the collectors of these transistors are getting voltage. So we definitely don't have a missing supply issue on that board. Now what we want to do is we want to know whether the problem is this side or this side here. And how we're going to do that is we're going to probe this area here, and we're going to look for a signal. So you want your transceiver in AM or CW mode. If you're in CW, you can use the key and close the key, or you can just grab a mic and push the push-to-talk button like I'm going to do. And we should have a carrier at this cable here if this section, previous to this point here, so the drive section is all working okay, we should have a carrier in this area. And a very simple place to look for that carrier would be on the base of both of these transistors, because really that's the input to those transistors. All right, so what I'm going to do is, of course, we have our radio hooked into a dummy load before we, push the push-to-talk, just in case, our RF power comes back or anything like that. You want to make sure that this thing is into an adequate dummy load. So what I'll do is I'm going to take my scope probe here, and I'm going to touch the base lead of both of these transistors. So I'll do this one first, and we'll look at the scope, and I'll grab the microphone and I'll push the push-to-talk, and again that's going to give us a carrier into this board, either in the AM or CW mode, depending whether you want to use your push-to-talk or the CW key. All right, so I only have two hands, so I'm going to have to focus the camera on the scope here. All right, now I'm going to grab my scope probe lead, and I'm going to touch it to the base of the output transistor here. All right, now I'm going to push the microphone here, and there's our drive signal. All right, about 3.5 volts or something like that, peak to peak. That's on one transistor. I'll let go of the microphone there. I'll move my probe lead over to the other transistor. This is the far side one now. I'll push the microphone again, And we have a drive signal there. Okay, so far we know that we have a drive signal coming to the bases of both of these transistors here. It's a really small signal, but we still have a drive signal at this base and at this base. Now, if these transistors are working, this is a collector, we should have a very, very large signal on this side here. Alright, so if we have a very large signal here, it's something beyond this that's gone wrong. If we have no signal here, and we have signal here, this device is most likely the problem. Okay, so what I'm going to do now is I'm going to grab my scope probe and I'm going to touch the collector, and we'll take a look at the scope again, and we'll see if we have any signal on the collector. Alright, so here's the microphone. I got the push to talk here. I'll touch the probe to the collector. Okay, you see that jump? That's because my scope is AC coupled. Alright, so I'm going to press the button here. And we really have no signal there. So now I'm going to go over to the base of this transistor and see what we have. And we have signal on the base and nothing on the collector. Now the collector has voltage on it. We know that it has 12 volts. So we can pretty much safely say that that transistor is finished. And we'll go over to the other transistor. This is the far side one. I'll touch the collector of the far side transistor. And I'll push the push to talk here again. And pretty much nothing there. And I'll go over to the base of that same transistor. And there we have our drive signal. So at this point here, we can pretty much say that those two power transistors, the RF outputs, are finished. So what we're going to do is we're going to open the leads, the base leads, because that's all we really need to do to check the transistors. And I'll show you how to check them one last test with the diode checker in your meter. So I'm going to have to disconnect all the power from the radio and make the chassis float. I don't want any connections on the radio whatsoever. The chassis completely floats whenever I do any soldering on here. And if you've ever worked with any solid state devices or anything like this, you'll know the importance of doing that. If there are any grounding issues between any of your equipment whatsoever, and you come in there and you have one, say a test lead clip to this thing that's connected to your scope, and you come in with your soldering iron and there's a little bit of a difference in the ground whatsoever, you can really zap a lot of components. So I think we've all done that, and it's a very, very safe thing to do. So whenever you do any work on these radios, you always want to make sure no power, no cables, no nothing applied to them. Basically, the chassis is going to be floating. That's the safest way to do things. All right. So one other check we're going to do here just before I go about doing all this here is we saw a pretty low drive signal on the base of these transistors here. Right now that's a really low, about 3.5 volts peak to peak. Now we know that the drive signal is coming out of this cable, going through this little transformer here, and then through the circuitry and into the bases of these transistors here. So if we take a look here, got my flashlight here, get my pointer, you'll see that there's a pad in there. You see that pad here? It looks like a 1206 part could be soldered at this point here. So this pad here is the ground side, and this pad here goes right to the center conductor of this cable. So now this really is the drive signal coming straight out of this cable before it goes through any of this network into the transistors here whatsoever. So what I'm going to do is I'm going to take my scope probe lead and I'm going to probe this, and I'm going to see what kind of a signal we have here, because we should really have a much larger signal at that point. Alright, if it's still a really, really low signal there, I would suspect that there may be some issues with the driver. But so that's what I'm going to do. So I'm going to take my probe here, and I'll just show you again. I'll take my probe lead here, and I'm just going to touch one of those little pads, those little 1206 pads in there. And we'll take a look at the scope here. So I'll move my camera up to the scope, and I need another hand. So here we go. Alright, I'm touching that pad. I'll push the push to talk here again. Whoa, you see we had a really big signal there. So let's see what, maybe turn this up to 10 volts per division. Okay. Wow, okay, 55 volts roughly, peak to peak. Alright, so we have no problems with our driver. There's a lot of drive just before that transformer. So that's something you're going to want to look for as well. So you're going to have a lot of drive signal there. Of course, now the radio's power is turned right up. So the pre-drive power is right up. And we know that's the kind of signal that you're going to have there. So there's about 55 volts peak to peak on that right now, on that first little pad down there. And of course, it's going to go through all this, and then it goes into the bases of these transistors. So we really don't know the fault mode of this, whether the bases are shorted or open or what's going on with these transistors here, but that's what we're going to do next. So I'm going to heat up my desoldering tool, disconnect the radio completely, and then I'll show you how to test these transistors to make sure that they are absolutely dead. You don't want to go buying these transistors for no reason and finding out that it's another problem, because these are very pricey components. I have the base lead of this first transistor desoldered. I've moved this resistor off to the side, and you can see how I've lifted the lead and it's separated from the trace, and I will show you on this one here how it's done, so you can get an idea of how this is lifted up. So basically what you're going to do is you're going to remove the resistor first, and then you're going to get a jeweler's screwdriver or something and just stick it underneath the leg, heat the solder up on the top of the leg of this transistor, and then bend it up, and then vacuum with a desoldering pump under here, or use a piece of solder wick to soak up the rest of the solder so that this isn't touching the circuit board. So really we have an open connection to the base lead. So I'm going to attempt to do this side on the camera and show you how this is done. So I'll get my soldering iron here. I'll come around my tripod. Hopefully you can see all this. So I'm going to heat up the base lead and just remove this resistor very first. Get this thing out of the way. Okay. So we can see that that's now out of the way, and we have the base lead exposed right here. Alright, so the next thing I want to do is I want to get under there with a jeweler's screwdriver and lift the lead. So you have to heat the solder up on the lead. Alright, you want to get, a very small jeweler's screwdriver, and then you're just going to lift that flat lead up when the solder is melted, just like that. And that's how easy it is. Now there's still solder joining this on the underside here. So I'm going to get my desoldering tool here, and I'll just vacuum up this solder so that it opens the connection. Like that. And now we have the disconnected base lead on this transistor. If I move the tripod over just a little bit here, you might be able to see how that's disconnected. And also lift it up. I think this is about as close as I can get with this focusing of this camera. So there we go. You can see that it's open under here now, and this is just free, and we can now test it. And that's what we're going to do next. I'm now ready to test the transistors using the diode test function in my digital multimeter. Since these are NPN transistors, I'll take the positive lead of my diode checker, touch it to the base, and I'll leave it there. I'll take the negative lead of my diode checker, touch the emitter, it should check as a diode, then I'll move the negative lead over to the collector and it should check as another diode. Doesn't matter which order you do this in, it should just check as two good diodes. If this was a PNP transistor, which it isn't, but if it was, it would be the opposite way. I would have the negative lead on the base, and I would touch the positive lead of my diode checker to the emitter, and it would check as a diode, and then again to the collector, and it would check as another diode. It doesn't matter the order you do this in. You can check the collector first, or you can check the emitter first. It doesn't really matter. We're just looking for two good diodes. So if you're interested in checking transistors this way and you want a little more information about this, I'll link in another video just below the Show More tab there. So click on the Show More tab, and one of my earlier transistor testing videos will be there for you. It'll also help you identify transistors by the numbering and lettering systems on them. So now keep in mind that when we're doing this test, there is no power applied to this radio whatsoever. The power is disconnected and the chassis is still floating. So again, since this is an NPN transistor, I'll put the positive lead on the base and I'll test these two leads as diodes. So I'll focus the camera on my meter here. It's in the diode test mode. Alright, the positive lead is on the base. I'll put the negative lead on the collector first and it should check as a diode, which it does. And then I'll take the negative lead and touch the emitter and it should check as another diode. and this transistor is faulty. The readings should be very close together and they shouldn't move like that. So again, we'll do that with the second transistor here. I'll take the positive lead of my diode checker, put it on the base. I'll touch the collector first with the negative lead, and then I'll touch the emitter with the negative lead, and we should get two good diodes. And the readings should be very close together, and they should be stable. So here we go. Positive lead on the base, touching the collector. So that's a stable diode reading there. Now I'll go over to the emitter. And we have another faulty transistor. So now we have to remove these transistors and replace them. So what I'm going to do is I'll just desolder these leads on the transistor the same way that I desoldered this lead right here. So basically heat it up, lift the lead up, and then vacuum underneath the leads. Undo these two screws and this transistor will just come right out. And it's the same for this transistor right here. There will be thermal compound underneath here. That will need to be cleaned off, and then I will apply new thermal compound to the new transistors. And when I install them, the leads will be flat like this, and they will align with the traces perfectly. And I'll resolder the transistors in just the exact same way that these things came out. And I'll show you the process of resoldering the leads here when I get the transistors in. I've now removed both the transistors, here and here, and I've cleaned up the traces with a Q-tip and some acetone to get rid of any remaining flux or resin residue. It's very important to do that because within that old resin or flux residue, sometimes little solder balls will hang out and short traces, and we definitely don't want that. This transistor here was a little bit more difficult to get out than this side here, just because one of the emitter leads is right underneath this wire that's coming out of the transformer here. So you don't want to move this wire around, it's very rigid, you want to leave that alone, so you want to work around this. So what I did is I lifted all the leads on this transistor, much like we did in the test, until I got to this emitter lead here. Then I removed the screws on the transistor and put my soldering iron on that lead underneath this wire, not touching the wire with the soldering iron, melted the solder and lifted the transistor up and out. Then of course there's a little bit of solder left on this trace, just like on all the rest of them after you do desoldering, and I can't get my vacuum tool underneath this wire, so I use some solder wick just to get rid of the rest of that solder. Now if you have a problem making your solder wick work and it's frustrating, a very good thing to do is just add a little bit of RA flux to the end of your solder wick before you use it, and it'll supercharge that solder wick and it'll work very, very well. So that's what I do before I use solder wick on anything. I just put a dab of RA flux on it before I put the iron on it, and it works extremely well. So that's all cleaned up, and then all the other pads are cleaned up like I mentioned with my vacuum desoldering tool. They all need to be very flat. You can't have any solder lumps on the traces because the new transistors that we're going to put in have flat leads, and if there's a ball there when we tighten the transistor down, the lead's going to want to lift like that, and that's no good. So that everything needs to be very clean and flat before we install these transistors. Now we're just about ready to install these transistors now, but we have to do one more thing before we do that, and that's check the bias circuit in this area to make sure that it's working okay, and we'll do that next. Before we go and install our two brand new RF output transistors here, we need to verify that the bias circuit is working correctly on this board. If the bias circuit has failed, we could immediately destroy our two brand new RF output transistors in the blink of an eye. So this is very, very crucial. Do not skip this step. So how this circuit works here is this little VR here is the idle current set, or the bias set. Alright, this little VR controls the little LM358 here, which is a little surface mount IC right under these wires. I don't know if you can see that on the camera. That little LM358 controls this transistor, and this transistor is what sets the bias to these two RF output transistors. So depending on the failure point of your two RF output transistors, this transistor here could be damaged. So it's very important that we check this circuit out. So now, in order to check this circuit out, we need to apply power to this radio right now. So again, if you're going to apply power to the radio and work on it, you're doing so at your own risk. You need to make sure that you have no solder balls or any bridges in here, and make sure that, no wires are touching and everything is nice and safe. So just take care. So with the power supply attached to the rear of the radio. We're going to turn the radio on. We're going to turn the radio to the lower sideband mode or upper sideband. It's absolutely fine. It has to be in the sideband mode. We're going to turn our RF power not right off, but we're going to turn it right down to 1. If you turn it right down to 0, this circuit won't come on. So we need to have it at least sitting at 1. And we also need to have the microphone gain at 0. So we want absolutely no mic gain at all. So again, upper or lower sideband, power sitting at number 1, basically off, one step from being off, and the mic gain at 0. Then what we're going to do is we're going to take our voltmeter, put it on DC volts, tie the ground of our voltmeter to the frame. We're going to take this VR here and we're going to turn it completely counterclockwise first. So turn this counterclockwise. Take the positive of your voltmeter and we're going to touch the base trace right here that attaches to the trace of the new transistor. We're going to grab the microphone and push the push to talk, and it should read about 0.5 of a volt. So here we go. There you see, 0.5 of a volt. All right. So I'm going to let go of the push to talk. It goes right down to 0 again. So far, so good. So now what we're going to do is take our screwdriver, put it into this VR, and turn it completely clockwise. And then we're going to repeat that step. We'll put the voltmeter probe on the base lead and push the push to talk, and we should have roughly a volt. And there we have it, 1 volt. No problem. So now we've verified that the bias circuit in this radio is working. So what we want to do is take this VR, just so we don't forget, and turn it right back to the fully counterclockwise position, so that when we install our 2 brand new RF output transistors, we're going to have a minimal amount of idle current. You never want to start that with it at the high end. Now, of course, they've limited the range by this. It only goes from 0.5 to 1 volt on the base, but when we have the transistors in here, that could really put us into a really high region of idle current. We don't want to do that. So again, we want this completely counterclockwise to start with our 2 brand new transistors in there. So that's what we'll do next. We'll get the transistors and install them, and then I'll show you how to set up the bias. It's time to play Identify the Fake Transistors. So these 2 here are the ones that have been removed out of the transceiver, and we know these 2 are genuine Toshiba components. So that should help you choose in the lot here which ones are fake and which ones are real. So I'll give you a moment to pause the video and stare at the screen and make your choice, and when I come back I'll show you what to look for. Alright, the ones by the blue dots are the fake ones. So how we can just very quickly with this lot tell the fake ones is the leads are very short on the fake ones here. That was the first telltale sign. We can see that they're cut extremely short. This one here is a real one, and this one is a real one. We can see that the length of the leads that come out of the device are much longer than this one here. And all the fake ones are like that. Some are a little shorter than others on the fake ones. Now, there's a whole bunch of things to actually look for on these devices to see if you have a fake one. And we'll have to go to the other table and we'll have to reposition the camera to show you that. On the ends, we have 2 real devices, and in the center we have 2 fake devices. We can immediately see the difference between the 2. On the real device, the leads are quite a bit longer. This is the fake device, and you see how short they are. It even looks like they've been cut on an angle with a shear or something like that. And the fake device also has some sort of weird corrosion happening on the legs. On the fake devices, we'll also notice that the name and the numbering system isn't quite centered like it is on the real device. You see here the stroke on the J of Japan here is centered with the center of the C, whereas on the fake device the J starts at the beginning of the C. On the real device, the number 2 is right centered to the beginning, right at the bottom of the A there. It's centered with the 2, and this last A here is centered with the last stroke of the N. On the fake device, the D is not centered with the last stroke of the N, and the 7 is right in the middle of the A. and it goes for this lot number here as well. So quite a few differences just right there alone. Now on the fake device, there's some sort of a gold that they've put down in here that can be scraped off really easily. Scrape it off with your fingernail. So that gold that's down in here is not common to a real device. It does not have any gold down in here whatsoever. The plating is also quite a bit different. This is a real device here, and this is a fake device, and under a microscope you can see the difference in the plating. Here you can actually see it just a little bit too. There's a little bit different color here to this fake device than to the real one. So there are quite a few differences in the fake to the real devices. Unfortunately, right now the market is absolutely saturated with these things, so you really have to be leery when you're ordering these things up. You want to go to a reputable dealer or somebody that's going to sell you genuine components that guarantees it. So these genuine devices here, these two brand new ones, are marked with a 45 on them, and these have been purchased from a really reputable parts supplier. Now I'm not sure what this 45 is, whether this is supposed to be the gain of the device or whatever, but they're both marked the same. They came in a bag and they're supposed to be a matched pair. So I'm going to throw these on the curve tracer, and we're going to check out and see how closely matched these supposed matched pair of transistors are. So it's very important to keep the matching of these close in this circuit. We want a really good matched pair of transistors there. If there's slight differences, it's not all that incredibly important, but we want them to be as close as possible. So we'll do that next. In the curve tracer, we have two genuine Toshiba RF output transistors purchased from a very reputable source. These came in a bag classified as a matched pair, and each one has the number 45 written on one emitter lead. So what that 45 means at this point, we really don't know, but we'll find out if it is a gain measurement, or maybe this is a secret code for them. I really don't know what kind of test they're performing on these. But what we will find out is how well matched these things are on an actual curve tracer. So I've got this set up right now. If I leave this thing doing the curves on one transistor for a while, the transistor will get a little bit warm, but it's a pretty safe test at this. So when we look at the screen here, each box this way is 10 milliamps, the bottom one being 0. So this line is 0. So we have 10 milliamps, 20, 30, 40, 50, 60, and so on up the screen. Each box this way is the collector voltage, and that will be 1 volt, 2 volts, 3 volts, 4 volts, and so on. And each step that you see on the screen will represent 0.2 of a milliamp or 200 microamps. So looking at this as 0.2 milliamps makes the math just a little bit easier, and that's what we're going to do. So we'll just do it that way. So what I'm going to do now is I'll turn it up. We'll test this one here first, make sure the switch is in that position. By clicking this switch here, all it's going to do is transfer from this side to this side here. So it's basically opening the 3 connections here and connecting these 3. So there really is, this is a really close test. All the lead lengths are all the same, and they're hooked up the same and everything. So this should keep things very, very close. All right, so here we go. I'll start this up, bring it up to about 10 volts on the bottom there. Alright, so we're looking at this one here. So we have 10 milliamps per box this way. So we have 10, 20, 30, 40, 50. This one's close to the line. We'll use this line. So say 51. We have 51 milliamps at this point, and each step is 0.2 of a milliamp. So 0.2, 0.4, 0.6. So we take 51 divided by 0.6, and we get the DC beta is 85 for this transistor here. Alright. So 85 for this one here. Now when I move this switch over to this side here, what will happen is, it's just going to move the leads over, and on this screen here, the traces should be exactly the same if these are a really good match. Like this won't move. It'll stay exactly the way it is. We'll just see a flicker as I go from the side. If we see a change in the pattern, we know that we have a gain difference right away. If it's more compressed, the gain will be a little bit lower. If it's a little bit larger, we'll have a little bit higher gain. Okay? So I'll click the switch, and we can see it got a little bit lower. I'll click it back to the other transistor, and click it back to this one here again, and we can see that we do have differences in these transistors. Okay, So if we do the calculation for this one, we're going to go 10, 20, 30, 40, 50. So we'll say 49, okay, by 0.6 again. Remember 0.2, 0.4, 0.6. So we go 49 divided by 0.6 is 81.6 is the DC beta for this one. So for this one here, we have 85 and we have 81.6. Now that's not exactly matched, but it is relatively close and I would say acceptable, but I wouldn't want to go any further than that because, you know, we don't want one device working a little bit more than the other. All right, it's always very important to have a matched pair whenever you're replacing these things. So they both say 45, and we can definitely see that there is quite a difference, 81.6 to 85. So being well matched, I don't know, but at least they're close enough to use. So what I'll do next here is I'll put in a, maybe I'll get some of the counterfeit transistors and we'll play with some of those for just a second. I've randomly picked two fake devices off the bench here and put them into the curve tracer. So there really was no thought behind this. I just reached down, grabbed them, put one here and put one here. So this test here could very accurately represent even if we had two original devices put into the curve tracer here. Because the differences between unmatched transistors are really all over the place, even between fake ones and real ones. So let's just take a look at this and this will give you an idea of the differences even if you were to have two unmatched original devices. So everything is all set up the same. I'll just buzz through this quickly here. Alright, so we're dealing with about 54 milliamps here by 0.6, which gives us a beta of 90 for this one here. So this one's 90, okay? I'll click the switch. You can see the difference on the screen, what a dramatic difference there is between the two transistors. Okay, we're on this one here right now. We'll say 47 by 0.6 gives us a beta of 78 for this one. So we're dealing with 78 to 90 here. We definitely wouldn't want these two working together. This one here would be doing all the work. Now again, even if these were original devices, we could get these results if they're not matched. Really the gain for these transistors being original or not really is all over the place. These are counterfeit devices and they look not bad on the screen. Would I ever trust them in service? Not a chance. Let's take a quick look at one of the faulty transistors out of the transceiver here. So I've got the switch pointed at this one right here and everything looks normal on the screen. So I'll move the switch over to the faulty one. And what we see on this screen right here is the result of an open emitter. What we're seeing is the base steps in here. Alright, so when I open the emitter on this one, you'll see we have absolutely no change. But if I remove the base connection here, you'll see that it goes away and it looks normal. Alright, so I'll go over to the good device, and we'll see everything looks normal. Now if I give this one the same failure point as this one by opening the emitter, it will mimic what we saw here. So there we go. That would be an open emitter. We go back and forth. Absolutely no change. So that's the failure point in this transistor right here, and that's what it would look like on the bottom scope there. It's the reason for this scope here is I can hook a transistor up and without even turning any sweep voltage up or anything, I can already know what the failure point is. The new transistors are installed and I've marked their beta on the top here. I've also cleaned the surrounding circuit board here again with acetone and a Q-tip. Remember, when you're cleaning this, you want to make sure that you clean very thoroughly between the legs of the transistors. You should be able to clearly see the circuit board. We don't want any resin residue or anything like that left over because those little solder balls can hide in there and cause shorts in the future or even immediately. You got to remember that this is going to be getting pretty hot, this particular section of the radio. This is the power amplifier. So when resin gets hot, it gets soft, and if there is a floating solder ball, that could be a disaster waiting to happen. A word of caution with the acetone around the printing on the top of these transistors, the ink is very sensitive to it. That was one swipe with a Q-tip will really take this ink right off. So it's worth noting, there's two other capacitors in here I figured that you may want to check. I checked them in here. They're in the feedback network. There's two caps right here and two caps right here. Alright, if these caps short, it will also put supply voltage on the base of these transistors, and that could be, a big problem. So you can see the path here, right? This is the collector. through these caps, through the resistor here, and then into the base. So if there is a short here, we could have some big problems. So you want to check these caps, and those caps are right under here. Alright, that's an important thing to do. I don't really think that the failure point of these capacitors is very high. You know, or the chance of failure would be very high, but still, it's worth checking. So we don't want to purchase any more of these. So now that this is all done, we're ready to do the bias. I'm now ready to set up the bias in the RF power amplifier here. Now, by setting this little potentiometer here, what I'm doing is I'm setting the idle current to these two transistors. Now, they say on the schematic here that they want bias 500 milliamps total, it says. Okay, so in a perfect world, that would mean 250 milliamps per device. Now, there are no jumpers to remove in here in order to set the bias up, and they've mounted the solder pad for the positive lead for the power amplifier very high on this board here, so really you can just put your soldering iron on it and remove it. So it looks like this is what they've intended people to do to set the bias up in this amplifier section. Now, in a lot of other transceivers, they have a jumper you just remove, and then you can put your current meter across it and set it like that. But to tell you the truth, I really like this system much better. There are no loose connections or anything, and this is a really solid high current connection. You have to remember that in this transceiver, this little section here is what's going to be pulling all the current in transmit mode. So that is a really nice solid connection. So I've got my current meter in line with this now. Alright, I've got a piece of copper soldered into the board here to where this wire was soldered, and then this just runs off to my meter. My meter is fused by a 1.25 amp fuse, so if anything was to go wrong in this section, that fuse would just go away immediately. Now you need to keep in mind that we're not going to be pulling any more than 500 milliamps when we adjust this, so if something was to go wrong, that 1.25 amp fuse would just go away. Now, in order to set the bias in this radio, we need to have it in the same condition that we did when we were checking this before. So again, the radio should be in lower or upper sideband mode, no microphone gain, and the power level set to number 1. So just about completely off. So we're not at 0 because this section won't turn on. We need it to be at 1. And again, absolutely no microphone gain. Alright, so what I'll do is I'll focus my camera on the current meter here. Alright, and in order to set the bias, we need to turn the radio on. And I have the microphone in my hand here, and in order to activate the area, I need to push the push to talk button. Alright, now I'm going to put my screwdriver into this VR here. Remember, this VR, you start completely counterclockwise and work your way clockwise. So this is all the way at one end, and that's the counterclockwise end. So I'm going to push the push to talk button here. And you see we're starting out at about 9.3 milliamps. So I'll turn this up, and it'll move up quite quickly. And we need to adjust this to 500 milliamps. Now this will move around just a little bit, so you can keep it keyed for just a moment and then adjust it back down again. It's very touchy right around the 500 milliamp mark. Now don't get too incredibly particular over, you know, if it's 499 or 501 or something like that. That's absolutely fine. Alright, so I've got it at 499, and if I breathe on it, it will probably move. So there we have it. The bias is now set, and it's just that easy. So I'll let go of the PTT button here. Okay. And I'll focus the camera back down on the radio. So now what we need to do is we need to get rid of this connection here again and resolder this wire back into the board. And at that point, we're ready to try out the radio. This Ten-Tec Eagle is now finished. But before I put the lid back on this transceiver, I need to verify that this RF amplifier section is working okay. So I've got the radio set to 28.5 megahertz. It's in CW mode. The power output is set to 100 watts. That 100 watts will go into this dummy load here and be read by this Roden-Schwarz meter over here. Now the reason I'm using the Roden-Schwarz meter is because it has a really nice peak reading feature. Alright, I don't have a CW key hooked up to this right now, so I'm just going to use the push to talk button on the microphone, and that will mimic a CW key. So here we go. About 99.9 watts. We're doing just fine. Alright, now I'll put this into lower sideband mode. Now in order to get a peak reading on lower sideband, I need to make some noise into the microphone. So I'll just say test, and we'll see what our peak is here. Test. 100.25 watts. This radio is working excellent, and now the best part, I get to put the lid back on. Well, here we are at the end of another troubleshooting and repair video. If you enjoy these types of videos, I encourage you to check out my YouTube friend Peter at the TRX bench. He does very much the same kind of troubleshooting and repair procedure that you've seen in this video. He's a very talented fella, so if you enjoy these videos, I'm pretty sure you'll enjoy his as well. So just below this video, you'll see a little Show More tab. If you click on that Show More tab, there'll be a link to the TRX bench under there. If you get a chance, check him out. I'm sure you'll enjoy it. So if you enjoyed this video, please give me a big thumbs up and hang around. I'm sure there'll be many more videos just like this in the very near future. So until that time, bye for now.